Hello everyone, I am Surya Revanth Ayyagari, working at Center for Physical Sciences and Technology in Vilnius, Lithuania. I am a PhD student in TERAOPTICS Innovative Training Network funded by European Commission. My research project or my PhD title is based on diffractive optics integration with terahertz detectors and emitters. Today I am going to talk about semiconductor basics and its application, and also some of the terahertz experimental setups that we work with in our terahertz laboratory. I'm sure most of you heard about basic semiconductors and what are the devices, because these are basically becoming predominant in today's world with both in electronic and optical regimes. So today let's have a basic review about the semiconductors and its uses. Semiconductors are the materials whose electronic properties are in between metals and insulators. They are not actually perfectly conductive material, or it's like perfectly resistant insulators. They have their conductivities within the range of 10 to the power of -4 to 10 to the power of 4 Siemens per meter, whereas metals has 10 to the power of 6 Siemens or 7, doesn't matter, and insulators has quite low conductivity. That's why we call them as these as semiconductive materials. And also their energy band gap is also ranges between 1 to 3 electron volts. And these semiconductors are mainly based on two types. One is intrinsic or pure semiconductors, and the second one is extrinsic or impure semiconductors. And now let's discuss about intrinsic semiconductors or pure semiconductors. The perfect examples of these semiconductors are silicon and germanium, which are fourth group elements in our periodic table, are the perfect examples of these intrinsic semiconductors. And you can see in this left figure the example of a silicon which is bonded, which has like 4 electrons. These electrons are loosely bonded with the nucleus, and they are ready to able to flow freely only in certain conditions. For example, if the temperatures are too high, the electrons are free to flow, and then this acts as a conductor. And when the temperatures are too low, this acts as a insulator. And in the right corner you can see the energy diagram of a silicon or fourth group element. You can see the Fermi energy level is you can say in the middle, and we have like conduction band filled with electrons, and we have like valency band with holes. The Fermi energy level is at medium level. Now let's move on to extrinsic semiconductors or impure semiconductors. In order to make these intrinsic semiconductors as a conductors, we need to add some of impurities, or we need to dope some of the impurities, usually from third or fifth group elements. Because why do you need this? In order to produce these semiconductors to be more conductive in nature. And now usually the amount of doping level will be approximately by adding like one impurity atom per 10 million atoms. The ratio of this amount is called doping. So now the doping techniques are based on two. One, we can dope with a fifth group element which has X amount of free electron, or we can dope with third group elements which has excess holes. Based on this type of doping, we can classify these extrinsic semiconductors to two types, which is N-type semiconductor, and the other one is a P-type semiconductor. Now let's see what is N-type semiconductor. Now these N-type semiconductors are formed when an intrinsic semiconductor or fourth group element such as silicon or germanium are doped with fifth group elements like phosphorus or arsenic. So now you can see in the left picture the phosphorus, which is fifth group element, has bonded with silicon, which is fourth group element, and now we have left over with one free electron from the phosphorus, which is ready to move freely. Now these N-type semiconductors are also known as donor semiconductors because they are ready to donate, or which has ready to donate electrons, or which has a free electron. The right hand side, you can see an energy diagram where the Fermi energy level has been shifted towards the conduction band, and which is also known as donor level because of excessive amount of electrons that are present in this N-type semiconductor. Now coming to p-type semiconductor, which are also known as acceptor semiconductors, because the fourth group element or the intrinsic semiconductors such as silicon or germanium are doped with the third group elements such as aluminum and gallium. Then they are left over with excess amount of holes. In the left picture you can see the silicon is bonded with an indium, which is third group element, and left with the excess amount of holes here, or the vacancy. And now in the right hand side you can see the electron energy graph where the Fermi energy level is shifted towards the valency band because of excess amount of holes, or that's why this is called as acceptor level or acceptor semiconductor, because they are ready to accept the electrons because of higher number of holes. Till now, we have discussed about what is N-type semiconductor and what is P-type semiconductor, which are electrically neutral. One with higher number of electrons and other one is with a higher number of holes. Now let's see what happens when they fuse together or merge together. Here is what interesting thing happens. So when they are fused together, the electrons from a N-type semiconductor start to migrate to P-type semiconductor, and whereas the holes from P-type semiconductor start to migrate to N-type semiconductor. This happens until the threshold limit reaches, or in other words, we can say when the semiconductors stops accepting the charge carriers. And this threshold level, or we form as a potential barrier, which is also known as a depletion layer, that is shown in the blue dashed line. And depending upon the applications, we can use this PN junction in different applications by applying external voltage, or by adding external power. We can use this PN junction diodes with PN junction semiconductors in different mobiles or laptops, and also embedded systems, or also in GPS systems, or for making of LED displays or lightning displays. Now let's see some of the terahertz experimental setups that we use in our laboratory. The first one is the terahertz imaging system. What you see here is the schematic representation of it, where the terahertz imaging system is composed of RF generator and amplifier as a terahertz source, which emits 0.6 terahertz and also 0.3 terahertz, where the beam is passed through collimated lens and some of gold mirrors and the beam splitter, and also parabolic mirrors to guide the beam, and finally it is detected by D1 and D2 detectors, where the D1 is the detector which collects the transmitted beam from the sample, where the D2 is a detector which detects the reflected beam from the sample, where you can get some of the imaging where we can get some of the imaging of the sample. And the second setup is a terahertz time domain spectroscopy, or terahertz TDS system, which we use quite common in our laboratory. And here you see the schematic representation of TDS system. The output of a femtosecond laser pulse is split into two beams by using a beam splitter, one as a pump signal and the second one is a probe signal. So the pump signal is used to generate terahertz radiation, and which is modulated with a frequency of f, and the other beam is routed through a delay line, and it is used to detect the terahertz beam. The black lines that is illustrated as the signal connections and inputting the modulation frequency, and the detected signal to a lock-in amplifier and to the PC, and where the amplitude with a time scale is detected in the PC, and then the FFT fast Fourier transform is performed in order to see in a spectral domain. Thank you.